Hello everyone, and welcome to this challenge question walkthrough for Edexcel's Pure Year 2 textbook, Chapter 9. Okay, our first question is from exercise 9a, and we're asked to prove from first principles that the derivative of sine of kx is k cos of kx, and we're told we can assume these things, so the formula for sine of a plus b, and as h approaches 0, sine of kh over h approaches k, and cos of kh minus 1 over h approaches 0. Okay then, so we can start by writing out the formula for differentiation from first principles, which we know is the derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And in this case, we're going to have the function we're trying to differentiate, f of x being sine of kx. And so applying the formula for differentiation from first principles in this case gives us that the derivative of f of x is equal to the limit as h approaches 0 of sine of kx plus h. Note that we've got sine of kx in f of x, and we're replacing the x with x plus h, so we need to multiply all of the all of the x plus h by the k. And then we're going to take away f of x, which is just sine of kx, and that's going to be all over h. And now at this point, the bit that's jumping out at me to try and work with is this sine of k lots of x plus h. It doesn't look particularly nice, but we are given a clue in the question, and that is we can assume the formula for sine of a plus b, which is sine of a plus b is equal to sine of a cos of b plus cos of a sine of b. And we can use that here if we expand out the brackets. So sine of kx plus kh by multiplying each of the x and h by the k. And that is then going to be equal to sine of kx cos of kh plus cos of kx sine of kh. Okay, then we can plug that straight into the limit. So the limit as h approaches 0 of, then we're going to have sine of kx cos of kh plus cos of kx sine of kh. Take away sine of kx all over h. And at this point, it's a good idea again to look back at the question, and we can assume that as h approaches 0, sine of kh over h approaches k, and cos of kh minus 1 over h approaches 0. And looking at this expression we've got down here, I can see we've got a sine of kh over h here, and we've also got a cos of kh minus 1 over h in these two terms here. So we've got the cos of kh and the minus 1 all over h if we take out a factor of sine of kx. And at this point it would be a good idea to split the limit up. So remember, we can do that if we're adding or subtracting terms. So if we first split the fraction up, keeping the same denominator. So remember, this is the same as the limit as h approaches 0 of if we group the green terms. So the limit as h approaches 0 of sine of kx lots of cos kh minus 1 from the green terms, factoring out a sine of kx, and that's going to be all over h. And then we can add the cos kx sine kh over h, and this is the same thing because they're fractions with the same denominator, so it's fine, we can split that up like that. So then we've got the limit as h approaches 0 of all of this, and we're happy because we've got these bits which we know what they tend to as h approaches 0. So at this point we can then split the limit up into two separate limits, just because we're adding the two terms, so it doesn't make any difference at all. So the limit as h approaches 0 are first of all sine of kx lots of cos kh minus 1 over h, and then again the limit as h approaches 0 of cos of kx lots of sine of kh over h. And there's a reason why I've written these bits out separately. So these are the same things as the terms up here, but just I've taken one of the factors from the numerator out in front, and that is because these here, the sine kx and cos kx, don't actually depend on h at all, because, well, they don't have an h in them. So we can actually factor these out of the limits and put them in front, just because they don't depend on what h happens in any way, shape or form. So we've got sine of kx times, then the limit as h approaches 0 of cos of kh minus 1 over h, plus, then taking out the factor of cos of k of x, times the limit as h approaches 0 of sine of kh over h. And now we know what these two limits are, because we're told we can assume them in the question. This one on the left goes to 0 as h approaches 0, and this one goes to k. So plug in those values in for the limits. We've got that the derivative of f of x is equal to sine of kx times 0 plus cos of kx times k. This term cancels, and so we're left with k cos of kx as required. Okay, and our next question is from exercise 9b. We've got a curve C that has the equation y equals e to the power of 4x, take away 5x, and we're asked to find the equation of the tangent to C that is parallel to the line y equals 3x plus 4. So first things first, if we know that the equation of the tangent is parallel to y equals 3x plus 4, then the gradient of the tangent must also be 3. So the gradient of the tangent is equal to 3, and that means that the derivative, so dy by dx, at the point of the tangent has to also equal 3. So let's find out what dy by dx is, and then set that equal to 3. So using the chain rule for e to the power of 4x, the derivative of 4x is 4, so that's going to go in front, and then we leave the e to the 4x as it is. Then the derivative of minus 5x is just minus 5. Okay, and we know that is equal to 3 at the point where the tangent is parallel to y equals 3x plus 4. Then we can rearrange, so 4e to the power of 4x is equal to 8. Dividing both sides by 2 gives e to the power of 4x equals 2, and taking ln of both sides at this point gives us 4x is equal to ln of 2, so x is equal to 1/4 ln of 2. So if you imagine the curve looks something like this for positive values of x, so when x equals 0, y is going to be equal to e to the 0, take away 0, so just 1, and then we're going to be increasing exponentially. Even though we have this minus 5x term, just because e to the power of 4x is going to grow much, much faster than 5x, so overall it's going to have the same sort of shape as an exponential graph. Okay, let's say this is the point here with x coordinate 1/4 ln 2. So we know that the gradient of the tangent at this point then is going to be 3. And we know that the x coordinate of this point, which is common to both the curve and the line, is 1/4 ln 2. And we can use the equation of the curve to find the y coordinate. So y equals e to the power of 4x, which is 1/4 ln 2. Take away 5x, which is again 1/4 ln 2. Simplifying this e bit, so we're going to have e to the power of just ln 2, which is just 2, cancelling out the e and the ln. Then we're going to have minus 5/4 ln 2. So the y coordinate is then going to be 2 take away 5/4 ln 2. So 2 take away 5/4 ln 2. And we're almost done. We just need to find the equation of the tangent. So let's call the tangent L. We're trying to find the equation of this line L. We know its gradient, we know a point on the line, so all we need to do now is substitute that in to y equals mx plus c, or the one I prefer to use, y take away y1, which is just any point on the line, equals the gradient, which is 3 lots of x minus x1, which is 1/4 ln 2. And just doing a little bit of simplifying then, being careful with negatives and brackets, we're going to have y equals, adding the 2 minus 5 quarters ln2 to the other side. Then we're going to have minus 3 quarters ln2 plus 3x, expanding out the bracket on the right hand side. And then tidying this up a little bit, we're going to end up with y equals 3x plus 2 minus 2 ln2. Okay, for exercise 9c, we're asked to find dy by dx given that for part A, that y equals the square root of sine of the square root of x. So, here we've got y equals, I'm just going to replace the square root signs with the power of a half, just to make it easier to see how we can differentiate this. There we go. The first thing we've got to do is look at the outermost function, which is something to the power of a half. And how we differentiate something to the power of a half is we need to take the power of a half down and then reduce the power by 1, keeping whatever is inside the same. So 1/2, take away 1 is minus a half. Then we need to multiply by the derivative of whatever was inside. So the sine of x to the power of a half. And now to find this derivative, again, we're going to have to use the chain rule. So the function that's outside this time is the sine, and the function that's inside is the square root of x, or x to the power of a half. So if we differentiate the sine part first, that's going to give us cos of the same thing inside, x to the power of a half. Then we need to multiply by the derivative of the inside again. So multiplying by the derivative of x to the power of a half, which is going to be a half x to the minus a half. So putting that all together, our answer is going to be a half times sine of the square root of x to the power of minus a half times then the derivative of sine of the square root of x we had was cos of the square root of x times the derivative of the square root of x, which is a half x to the minus a half. So if we simplify this a little bit by putting these constants a half and a half together, giving us 1/4, then I guess we can combine these two terms here if we wanted to, because they're both to the power of minus a half. So if we multiply them together, we're going to have x sine of the square root of x, or to the power of minus a half, times cos of root x. And then also if we wanted to, we could rewrite this as one fraction if we take this this negative power down. So we could write this also as cos of the square root of x on the top, and then the 4 and the square root of x sine of root x on the bottom. And then for part B, we've got ln of y equals sine cubed of 3x plus 4. So there are two different ways in which we could approach this question. One uses implicit differentiation, which is covered later on in this chapter. And the other one is just to raise each of these sides, raise them as powers of e. So we would have e to the ln of y is equal to e to the power of sine cubed of 3x plus 4. Then on the left hand side, the e and ln would cancel out, and we're just left with y equals e to the power of sine cubed of 3x plus 4. Then we could differentiate from there, or if you know how to do implicit differentiation, we could take the derivative of both sides of this equation, and then we'd have on the left hand side, differentiating ln of y is 1 over y, and then we need to times by the derivative of the inner function, which is y, so times by dy by dx, and that would equal the derivative of sine cubed of 3x plus 4, and they will give you the same answer, but they're just slightly different. But for the sake of this video, I'm just going to focus on this method on the left down there. Okay, so we've got y equals something now, so we can differentiate both sides. So we're going to have dy by dx is then equal to, right. And again here we're going to have to use the chain rule a couple of times. So let's start with the e part. The inside function here is going to be this sine cubed of 3x plus 4. So when we differentiate e to the power of something, we keep that the same. So e to the power of sine cubed 3x plus 4 remains, and then we times by the derivative of the inner bit, the sine cubed of 3x plus 4. Okay, now at this point we need to do the same thing again with this up here, because we've got more nested functions. So remember, this is really saying sine of 3x plus 4 all cubed. So to differentiate this bit next, we need to think of it as being something cubed. So this is the inner function here, and it's being cubed. So when we differentiate this, we're going to get 3 lots of sine squared of 3x plus 4, reducing the power by 1, and times in by the initial power by the 3. Then we need to times by the derivative of whatever's inside again, which is the sine of 3x plus 4 this time. And we need to use the chain rule one more time in this case. So taking the inner function to be the 3x plus 4 this time, the derivative of sine of something is always going to be cos of that same thing. So cos of 3x plus 4. Then we're going to multiply by the derivative of the inside, which is just 3. And then we're done. And again, writing all this out, we're going to have e to the power of sine cubed of 3x plus 4. Then we're going to multiply by the derivative of sine cubed of 3x plus 4, which was this here. So the 3 sine squared of 3x plus 4. And then we're going to multiply by, once again, the derivative of sine of 3x plus 4, which was 3 cos of 3x plus 4. And now we could do a little bit of simplifying with the constants again here and here. So we're going to have 9e to the power of sine cubed 3x plus 4, sine squared 3x plus 4, cos of 3x plus 4. Okay, and for exercise 9D, we're asked to find the derivative of these following functions once again. And the first one is y equals e to the power of x, sine squared of x, cos of x. Okay, so for this one, we're going to have to use the product rule a couple of times, just like in the last exercise with the chain rule. So y equals e to the x, sine squared of x, cos x. We can decide how to split this up. It doesn't really matter. I'm going to say I'm going to have this e to the x and then this sine squared x cos of x being separate. So if we let this be our u, the e to the x, and then this sine squared x cos x be our v, then the product rule says the derivative of this is going to be u, which is e to the x, times the derivative of sine squared x cos x, plus v, which is sine squared x cos x, times the derivative of u, which is actually just e to the x. Okay, and then we're going to have to use the product rule one more time for this here. So let's say the sine squared of x is our u and the cos of x is our v. So the derivative is then going to be u, which is sine squared x, times the derivative of v, which is minus sine x, plus v, which is cos x, times the derivative of u, and here we're going to have to use the chain rule. So this is the same thing as sine of x all squared. So if we differentiate that, that's going to give us 2 times sine of x to the power of 1, or just sine of x, and then we need to times by the derivative of the inner function, this sine of x, which is cos x. Okay, so if we simplify this a little bit before we plug it back in, sine squared x times minus sine x is minus sine cubed x. And then we've got here plus cos x times 2 sine x cos x, or 2 sine x cos squared x. So plugging this all back in, we're going to get e to the power of x times the minus sine cubed x plus 2 sine x cos squared x. Then if I just bring the e to the x to the front, we've got e to the power of x sine squared x cos x. Okay, and just to make this a little bit more tidy, we can take out a factor of e to the power of x. And on the inside, we're going to be left with minus sine cubed x plus 2 sine x cos squared x plus sine squared x cos x. And at this point, we can also factor out a sine x. So in the front, we're going to have e to the power of x sine x times minus sine squared x plus 2 cos squared x plus sine x cos x. And you could also rewrite the minus sine squared x as minus 1 minus cos squared x, and then simplify that to give you e to the x sine x times, then we're going to have cos squared x plus 2 cos squared x, which is 3 cos squared x, take away 1 plus sine x cos x. Any of these answers would be acceptable. And now for this part of the video, for some reason, my microphone decided to cut out only for this part of this exercise. So you have to bear with me, just walking you through what I've done here. So again, we're going to use the product rule for part B. I've let the first part in red there be u and the second part be v. And I'm just doing u times the derivative of v, and then v times the derivative of u. And for the derivative of v, we're going to have to use the chain rule, so bringing the power down and then taking 1 from the power, then multiplying by the derivative of the inside, which is minus 4. And then for the second one, we're going to use the product rule again. So u there times the derivative of v using the chain rule. And then we've got v times the derivative of u, which is just 1. So it's just v by itself. And then I'm just rewriting what we've got up there using the derivatives that we've worked out and simplifying a little bit along the way. Okay, and now I'm going to factorize out some factors of 4x minus 3 and 1 minus 4x. So the maximum number of 4x minus 3s I can take out is 5, and for 1 minus 4x the maximum is 8. And I've just done that here. Now we can just simplify what's inside those big brackets there. And then once I've done that, I then multiply out what's inside those brackets to form a quadratic, just to simplify things out a bit. And luckily, the original audio of the video is coming back right now. Then looking at the longer bracket, if we collect like terms, the x squared will give us minus 256x squared, and the x terms gives us 148x, and then the minus 3 stays the same. And that is our answer. Then moving on to exercise 9h, we've got a curve C with implicit equation 6x plus y squared plus 2xy equals x squared, but A asks us to show that there are no points on the curve such that dy by dx equals 0. Part B says find the coordinates of the 2 points on C such that dx by dy equals 0. So let's go ahead and differentiate implicitly then. So taking the derivative of both sides of the equation will give us, on the left hand side, that's just 6. Then to differentiate something squared, it's going to be 2 times that something to the power of 1, or just 2y here. And then we need to times by the derivative of the inside, which is y, so dy by dx. And then we need to use the product rule for 2xy. So let's say 2x is the u, and y there is the v. So u first times the derivative of v, so dy by dx. Then v, which is y, times the derivative of u, which is just 2. And then on the right hand side we simply have 2x. Now we need to get dy by dx by itself, so let's bring all the terms with no dy by dx to the right hand side, and then factor out dy by dx on the left hand side. So we've got 2y dy by dx plus 2x dy by dx. factoring out the dy by dx there. Then we can take the 6 and the plus 2y to the right hand side, so 2x minus 2y minus 6. Then we get dy by dx equals by dividing by 2y plus 2x, and we can also divide by 2 while we're at it. So these 2's will cancel out, and this 6 will become 3. So we've got dy by dx equals x minus y minus 3 all over x plus y. So this is dy by dx in terms of x and y. We now need to show there are no points on the curve such that this is equal to 0. So if we need this to be equal to 0, then it must be that the numerator, x minus y minus 3, is equal to 0. So we have y is equal to x minus 3. So if we have at any point on the curve C, y being equal to x minus 3, then we know that we've got a point on the curve for which dy by dx is then therefore equal to 0. So we then need to show that there are no points that are common to both the curve C and the line y equals x minus 3. So for example, say the curve C looked like this at some point. Then we need to show that y equals x minus 3, which would look something like this, doesn't intersect the curve at any point. Otherwise, at some point, we'd have that y is equal to x minus 3. So therefore, x minus y minus 3 would be 0, and then the derivative would be 0 at that point. So we can do that by solving these two equations for the curve, and then for this y equals x minus 3, the line, we can solve them simultaneously, and we need to show there are no solutions. And I think the easiest way to do that would be to substitute the y equals x minus 3 into the equation for the curve. So we're going to have 6x plus y, which we know is x minus 3, if dy by dx is equal to 0, squared, plus 2xy, which is x minus 3 again. That is equal to x squared, which is just x squared. Okay. We can then go through here and expand the brackets. So 6x plus x squared minus 6x plus 9 plus 2x squared minus 6x is equal to x squared. Then we can cancel out this 6x and minus 6x, and this x and that x. So the quadratic equation we're left with is 2x squared take away 6x plus 9 is equal to 0. And again, remember, we're looking to show that there are no solutions. So the discriminant is equal to b squared, which is minus 6 squared, minus 4 times 2 times 9, which is 36, take away 72, which is minus 36, which is less than 0. So there are no real solutions, and so no points of intersection. And because we've shown there are no points of intersection, so there are no points on the curve for which y is equal to x minus 3, so there are no points on the curve where the derivative is then equal to 0. And then for part B, we're asked to find the coordinates of the 2 points on C such that dx by dy is equal to 0. Well, we know that dx by dy is just going to be the reciprocal of dy by dx. So dx by dy is going to be equal to x plus y over x minus y minus 3. So now we need to find the points for which x plus y is equal to 0 here. Or in other words, y is equal to minus x. And again, we do the same job of solving this equation here simultaneously with the implicit equation for the curve. So plugging that into C's equation again, we're going to have 6x plus y squared, y is minus x, so minus x squared is just x squared, plus 2xy, so 2x lots of minus x is equal to x squared. So 6x plus x squared minus 2x squared is equal to x squared. The x squareds on both sides cancel. So then on the right hand side we now have 0. Then we can factor out the left hand side to give us 2x lots of 3 minus x is equal to 0. So we've got either that x is equal to 0 or x is equal to 3. So that's a good sign. We've got 2 points. We just need to find the y coordinates now. So plug in these values of x back into the implicit equation for c. When x equals 0, we've got 0 plus y squared plus 0 is equal to 0. So y must be equal to 0. And then for x equals 3, we've got 6 times 3, which is 18, plus y squared, plus 2xy, which is 6y, is equal to x squared, which is 9. Then that gives us y squared plus 6y plus 9 is equal to 0. And then we can factorize this as y plus 3 squared being equal to 0. So then we get y equals minus 3. And our 2 points of intersection of the line y equals minus x and the curve c, or in other words, points on the curve for which dx by dy is equal to 0, are going to be 0, 0, and 3 minus 3. Okay, and for exercise 9i, question 1, we're asked to prove that every cubic curve has exactly 1 point of inflection. So, first of all, a point of inflection is any point on a curve. So let's just look at y equals x cubed as an example. So y equals x cubed looks something like this. And the point of inflection is right here at the origin for y equals x cubed. And that is the point at which the graph changes from being concave. So for negative values of x, the graph is concave. As you can see, this sort of cave-looking shape, as the gradient of the curve is decreasing. And then for the right portion of the graph, where x is positive, the graph is convex, as you can see, a sort of bowl sort of shape. And the gradient of the graph is instead increasing. So convex for that second part. And we're asked to prove that every cubic curve has exactly 1 point of inflection. And at this point of inflection, we know that the second derivative must be equal to 0, because for concave parts of the graph, the second derivative, the rate of change of the gradient is negative, because the gradient is decreasing. And for convex parts of the graph, the second derivative is going to be greater than 0. So at a point of inflection, where a graph changes from being convex to concave, or concave to convex, the second derivative must be 0. However, we've got to be careful, as this here, the second derivative being equal to 0, is not a sufficient condition. Which means that if we know the second derivative is 0, it doesn't necessarily mean that that point is a point of inflection. We've got to check that on either side of that point, the second derivative is going to have different signs, so that we know for sure that we're changing from concave to convex, or convex to concave. So it might be a good idea to start with the general equation for a cubic. So let's say we've got y equals ax cubed plus bx squared plus cx plus d. And then let's differentiate this twice. So first we have dy by dx being equal to 3ax squared plus 2bx plus c. And then the second derivative is going to be 6ax plus 2b. And we know this has to be equal to 0. So we've got that x is equal to negative 2b over 6a, or just minus b over 3a. Okay, and that is the x-coordinate of the 1 point of inflection, but we've got to check that it is actually a point of inflection for all cubic curves. And to do that, we need to have a look at the second derivative just on either side of this x-coordinate. And a way to notate a tiny little change either side of x is to write x plus or minus epsilon, which just represents like a really slight increment on either side. So for epsilon being greater than 0, we need to check the value of the second derivative at x being equal to minus b over 3a plus or minus epsilon. Just a really small change. Okay, so let's check what the value of the second derivative is, where we have x being equal to minus b over 3a plus epsilon first of all. That is going to be equal to 6a lots of x, which is minus b over 3a plus epsilon plus 2b. Then if we expand the brackets here, 6a times minus b over 3a is going to be just minus 2b plus 6a epsilon plus 2b. And the 2b's here will cancel, so we're left with just 6a epsilon. And now if we do a similar sort of thing with the other case, where we had x being on the other side of the point of inflection, so x equals minus b over 3a minus epsilon, then we're going to get 6a lots of minus b over 3a minus epsilon plus 2b. So we have, again, minus 2b, this time minus 6a epsilon plus 2b. And again, the 2b's cancel. And so you can see that we've got the second derivative at minus b over 3a plus epsilon being plus 6a epsilon, and the second derivative at minus b over 3a minus epsilon being minus 6a epsilon. So the second derivative definitely swaps sign. So we are definitely 100% sure that every cubic curve has exactly one point of inflection at x equals minus b over 3a. And for question 2 from this exercise, we've got a very similar sort of job to do. So here we've got the quartic curve, the general quartic curve, and we're asked to show that it has at most 2 points of inflection. So again, let's differentiate this twice. So dy by dx, first of all, is going to be 4ax cubed plus 3bx squared plus 2cx plus d. And then finding the second derivative, we're going to have 12ax squared plus 6bx plus 2c. And for a point of inflection, we need this to be equal to 0. And because this is a quadratic equation, we know we have at most 2 solutions. So at most 2 points of inflection. Perfect. Now for part B then, we need to prove that if 3b squared is less than 8ac, then c has no points of inflection. So if we have no points of inflection, then that means we have no solutions to the quadratic. So the discriminant, which is b squared, which in this case is 6b all squared, take away 4ac, so 12a times 2c. That is equal to 36b squared, take away 108ac. And we know for no solutions, the discriminant has to be less than 0. Okay, and then we can just rearrange, divide through by 12 to give us 3b squared is less than 8ac as required. Okay, and finally, from mixed exercise 9, the curve C has parametric equations y equals 2 sine 2t and x equals 5 cos of t plus pi over 12. And for part A, we're asked to find dy by dx in terms of t. So, to find dy by dx parametrically, we can find dy by dt and then multiply that by dt by dx, as these dt's sort of cancel out. So dy by dt then is going to be, 2 sine of 2t. The derivative of that with respect to t is going to be 4 cos of 2t, using the chain rule there. So times it by the derivative of the inside, which is just 2. Then dt by dx is going to be equal to 1 over dx by dt. And dx by dt there, again using the chain rule, but in this case the derivative of the inside function there, t plus pi over 12, is just 1, so it won't make any difference. That's going to be minus 5 sine of t plus pi over 12. And we can rewrite that as a single fraction by putting this 4 cos of 2t on top. And if we take away the minus in front, just to make things look a little bit neater, that is our dy by dx. Okay, and for part B then, find the coordinates of the points on C where dy by dx is equal to 0. So for dy by dx to be equal to 0, we need the numerator of dy by dx to be equal to 0. So this for cos of 2t has to be equal to 0. So cos of 2t must be equal to 0, dividing both sides by 4. And we know we're looking in the interval between 0 and 2 pi. So that means that 2t has to be between 0 and 4 pi, multiplying through this inequality by 2. So if we draw a graph of cos of 2t between 0 and 4 pi, that's going to look like this. So here from 0 to 2 pi, and then once more from 2 pi to 4 pi. So there's 4 pi, there's 2 pi. So we have solutions here, 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 and here. And they are going to be at pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. So if 2t is equal to pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2, that means that t is going to be equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And all we need to do now is plug these values of t back into the original parametric equations to find the x and y coordinates. But I'll save you the bother here. We're going to have the 4 points corresponding to these values of t being 5 halves 2, minus 5 root 3 over 2, minus 2, minus 5 halves 2, then 5 root 3 over 2, minus 2. Okay, then for part C, we're asked to find the coordinates of any points where the curve cuts or intersects the coordinate axes and determine the gradient of the curve at these points. So, where the curve cuts or intersects the coordinate axes, we know that y has to be equal to 0 or x has to be equal to 0. So for intersections with the y-axis, we need to set x equal to 0. Then we know that from the parametric equations, 5 cos of t plus pi over 12 must be equal to 0, or just cos of t plus pi over 12. And again, if we're looking for values of t between 0 and 2 pi, then t plus pi over 12 is going to be between pi over 12 and 25 pi over 12. So let's draw a graph to help us again. There we go. Between pi over 12 and 25 pi over 12, if we start from t equals 0, I'm just going to go slightly past 2 pi, and we're looking between here, so pi over 12 being at that point there, and here, this being 25 pi over 12. So where the curve equals 0, it's just going to be these two bits there. So t plus pi over 12 is going to equal pi over 2 or 3 pi over 2. So t at the points where the curve meets the y-axis are therefore going to be pi over 2 take away pi over 12, which is 5 pi over 12, or we're going to have 3 pi over 2 take away pi over 12, which is 17 pi over 12. Okay, so we know that the x coordinate is going to be 0. The y coordinates, we just need to plug these values back into the equation for y, the parametric equation for y. So here we have x being equal to 0, y is equal to 2 sine of 2t, so 5 pi over 6, which is 2 times a half, which is just 1. And for 17 pi over 12, we've got y is equal to 2 sine of 17 pi over 6, which is a half. So again, 2 times a half is equal to 1. So we've actually got this curve intersecting the y-axis at the same point, 0, 1, twice. But it turns out if we work out the gradients at each of these points, they turn out to be different. So dy by dx, which we calculated before, was equal to minus 4 cos of 2t over 5 sine of t plus pi over 12. If we plug in t equals 5 pi over 12 into the formula for dy by dx, then we actually get the gradient is 0.693 to 3 decimal places. But the gradient, if t equals 17 pi over 12, is actually minus 0.693. So if we think about what might be happening here, we know we intersect the y-axis only twice, and it must be at the same point. So the graph must end up looking something like this, where we have the graph intersecting the y-axis at 0, 1. So it must do something like this, where it goes, first of all, upwards like this, with a positive gradient, where t equals pi over 12, so t equals 5 pi over 12. Then it must come back round, and then intersect once again, so something like this, and intersect once again with the same but negative gradient. So we know we're looking at some sort of loopy curve, which many parametric curves are. So those are the two gradients. For part D, we're then asked to find the coordinates of the points on C where dx by dy is equal to 0. So dx by dy is the reciprocal of dy by dx, so it's going to be minus 5 sine of t plus pi over 12, so I'm running out of space there, over 4 cos of 2t. So for this to equal 0, we need the numerator again, so that's going to be 5 sine of t plus pi over 12 this time. That has to be equal to 0, or just sine of t plus pi over 12 needs to be equal to 0. And if we draw a graph of that, I'll do it down here. So sine of t plus pi over 12, sine graph looks something like that. And again, we're looking between 0, or here pi over 12, between t plus pi over 12 and 25 pi over 12, just as we were with cos of t plus pi over 12. So we can extend the sine graph just a tiny bit further and say that point there is our 25 pi over 12, and here was our pi over 12. And we're looking for solutions in this interval, so it's going to be here and here, where sine of t plus pi over 12 is equal to 0. So we've got t plus pi over 12 is equal to, that there is pi, and that there is 2 pi, so pi or 2 pi. So we have solutions t equals pi minus pi over 12, which is 11 pi over 12, and 2 pi take away pi over 12, which is 23 pi over 12. And again, substituting them back into the parametric equations at the top here, these two, then we get 2 points for which the gradient, the reciprocal of the gradient, dx by dy is equal to 0. They are minus 5, minus 1, and 5, minus 1. Okay, so just to summarize everything we've learnt about this parametric curve before we move on to part E to sketch the curve. So from part B, we learnt that 5 over 2, 2, minus 5 root 3 over 2, minus 2, minus 5 over 2, 2, and 5 over 3, 2, minus 2 were the points where dy by dx is equal to 0, or the gradient is flat. Then from part D, we learnt that the points minus 5, minus 1, and 5, minus 1 were the points where dx by dy is equal to 0. And this is where the gradient tends to infinity, so it's going to be completely vertical. Then in part C, we learnt that the curve meets the y-axis at the point 0, 1 twice, with gradients of opposite signs. And I've just realised I've forgotten to find where the curve cuts the x-axis, but it would be a similar process setting y equal to 0. So 0 equals 2 sine of 2t, finding all the solutions for t and plugging them back in. but from the solution bank, the points where the curve are going to meet the x-axis are plus or minus 4.830 and plus or minus 1.290, just following the exact same process as we did for the x coordinates. Okay, and then the gradients also follow a similar sort of pattern. So the gradients for these points are minus plus 3.09. So that just means that where we have the point plus 4.830, the gradient is minus 3.09, and the same vice versa. So the point minus 4.830 has gradient plus or positive 3.09. And then for plus or minus 1.290, the gradient, again, very similarly, is minus plus 0.828. Both of those two 3 significant figures. Okay, so that is all the information we've learnt from the first 4 parts. Now, the big bit, we need to sketch the curve using all of this information. So if I quickly draw some axes, here we go. So first, let's use the information from part C. So we're going to intersect the y-axis just once at the point 0, 1, and we're going to have gradients of opposite signs. Then let's go with the roots, so where y equals 0 along the x-axis, and that's going to be at plus or minus 1.29, so about there and there, and then also plus or minus 4.83, so further along there and there. Okay. Then we need to use the points where the gradients are vertical and flat. So let's use part B first. The points where the gradients are going to be flat are 5 halves, so somewhere in between there and 2, so about, let's say, there. That's where the gradients can be flat. And then also minus 5 halves 2, so on the other side. Then we're going to have 5 root 3 over 2, which is just less than 5. So the gradients are going to be flat about there and also there. Then looking at where the gradients are vertical, that's going to be at minus 5, minus 1, and 5, minus 1. So somewhere there, just past the root of 4.83, and also somewhere there. Okay, and now we just need to join up the dots, really. And we know we need to intersect there on the y-axis at 1 point only, so we're going to go something like that. Okay, and similarly for the other side, those are the 2 opposing gradients. So then we're going to keep going along to meet that point there and that point there. Keep going round until we get a flat gradient again here, and also a flat gradient again there. Then following the rest of the lines, we need a vertical gradient here and here. We need to intersect at the point there and then reach back up there. A flat gradient again, and I haven't drawn it the best on that side. I'll try that again. Around like that. And that is our graph. You could label the points on there if you wanted to. So that's 1 there. That is 1.29, minus 1.29, 4.83, minus 4.83. And that is your graph. And that is the end of this mammoth question walkthrough for Edexcel's Pure Year 2 Chapter 9. I hope you enjoyed this video. Please consider subscribing if you like this content and you found it useful. And I'll see you in the next video.